Hello everybody, this is Mike Bartles from the Hydrologic Engineering Center. This video is a recording of a webinar which took place on July 23rd, 2026. Within this video, I make a presentation entitled Hydrology and Hydraulics 101, or H&H 101, to a group of floodplain managers from the Pacific Northwest. As part of this presentation, I describe some basic information pertaining to H&H, including what types of questions are answered by practitioners of these subjects, how floods can occur, why H&H models are used, and how everyone can work together to better inform the interpretation of results. I also touch on statistical hydrology and direct viewers to additional U.S. Army Corps of Engineers H&H resources. Enjoy! My name is Mike Bartles. I like in all my presentations to lead off and include throughout the way pictures of rivers, pictures of dams. So if you have any idea of where we are in the world, or where this specifically is, throw in the chat. I'll do my best to try and keep an idea of what's going on in the chat and do both. It is in Alaska, yes. You should name that river in particular. Beautiful one. So, throw it out there. Like I said, I'm going to be talking about hydrology and hydraulics. Let's keep it like as a 101 style. I won't overwhelm you with equations, I promise. I don't think I have any equations in here, which I think everybody would appreciate. But I do want to emphasize the fact that H&H, hydrology and hydraulics, they're two sides of the same coin. We simplify the real world in slightly different ways, but the underlying principles are the same between the two. Since we need to treat expectations in terms of like probability, very familiar with like 1% annual exceedance probability type of thing. Since we need to tie it all back together, it's impossible to avoid the statistical aspect of that. But we'll mention that briefly as well. And also point out a couple of USACE H&H resources that you can always reach out to for help as well. All right, I'm on the right-hand side here in this image. It's me, but I do want to point out somebody who helped me a whole lot in this presentation, developing this presentation is Greg Karlovitz. Up until late last year, we worked together here at HEC. He left the federal service shortly thereafter, but I definitely wanted to call him out and say thank you, Greg, for helping me put all these materials together. We collaborated a lot on this one. All right, first, let's talk about hydrology. Name this dam also. I'll answer the last one. There's the Chulitna River. So it flows south out of the Alaska Range, and actually eventually joins with some other rivers in Talkeetna, Alaska, and eventually flows down past Anchorage. So you guys are pretty close on that one. All right, name this dam. Those in Canada, for sure. You need to call this one out. Yeah, Talkeetna's a beautiful place. All right, hydrology, first and foremost. Hydrologists deal with how much water is going to get to a specific place or places and when. Think of this as like a much more rough approximation of hydrometeorological processes as well. We're really looking at the occurrence of precipitation, whether it's going to be precip or snow. What is it going to do once it hits the ground in a large sense? How much is going to get to reservoir X? Am I going to have to deal with it now? Am I going to have to deal with it 3 weeks from now? How much is going to go into the ground? That type of thing. Much more broad strokes as well. So the previous picture was Mica Dam on the Columbia River. It's part of the sequence of dams that Canada built to serve massive purposes for the Columbia River Treaty. Now name this one as well. This one's in Wyoming. I'll give you a guess. I think the spillway is absolutely awesome in this one. Not too many other spillways look like this. All right. Before we delve into hydrology and hydrologic modeling in particular, let's talk about some terminology first, so it'll make sense what comes later on. Hydrologists typically deal with watersheds, and that would be any polygon, any area where if water melts, falls from the sky, whatever, it'll go to a common place, right? So that's signified in this image on the right-hand side with this purple polygon, right? If water falls along the ridgeline, which is the uppermost part of this watershed, if water falls here, it'll eventually get down to this point, right? If water falls here, it'll eventually get down to this point over here. If water falls way over here, it's not going to get to that point. It's not part of that same watershed. These ridgelines signify the boundaries of this watershed. The upper parts of the watershed we refer to as the headwaters, right? So that's basically all around the periphery of this watershed. Precipitation, either in the form of melting snow or liquid rain falling from the sky, whatever, all first goes into these tributaries. These upper parts of these streams are typically very, very steep, right? And the slopes start to mellow out as you get further downstream and enter into really areas that we like to regulate, where people live, property is placed. Consequences are typically high within floodplains that surround, say, a main stem river, where this thing empties out into the ocean, or the most downstream point of it we typically refer to as an estuary. Right? A lot of things happen within watersheds. You've seen cartoons of the water cycle before. Here's just a really well enumerated one from the USGS. Water in the form of water vapor originates in oceans and other water bodies. This radiation from the sun, eventually originally from the sun, causes all this stuff to evaporate into the air or transpire from plants. That coalesces into clouds, either through uplift processes or orographic processes. Whatever falls back to the ground as either solid or liquid. Some of that water eventually goes into the ground, runs off on the overland plain. That water then that goes into the ground doesn't just disappear. Usually it comes back out somewhere, somehow, some way, forms in rivers and goes into bigger streams and maybe some lakes along the way. Some of it freezes and forms glaciers and stuff like that. A lot of stuff that happens in here, right? As hydrologists, we break this up into a lot of discrete steps. Greg added that one in the lower left-hand corner with the bug eyes. Yeah, looks rather complicated, right? But the reason that we do this is that it allows us to discretize the problem into unique processes that I can simplify to my heart's content. So say maybe I really want to be super accurate with how I represent precipitation, right? But I don't really need to worry about too much complications once it hits the ground. I'm just going to say a certain amount of water goes in, a certain amount of water doesn't. I can really use complicated processes to represent the precipitation phase, but then I don't have to really use complicated stuff once it gets to the soil. Maybe you want to use more complicated process over here. This is how hydrologists think. This is particularly how engineers think, right? I like discrete steps along the way gates that I can go through to solve specific problems. We represent all of these processes in the modeling applications that we use along the way to quantify how much water gets here and when. Also, before we go further to talk specifically on modeling concepts, let's also talk about how floods occur, right? In a nutshell, it's when more water is provided to a watershed than can be readily infiltrated or stored somewhere, right, within a reservoir, something like that. There's a great example of a flood that occurred in, I think it was 2019, not too far from where I lived. So this was back to back to back atmospheric rivers that made landfall. I think within like 10 days, we had 3 of them in very short succession to one another, very, very quickly, right? That doesn't always happen because of back to back to back storms or a lot of rain falling from the sky. It can happen from melting snow, right? Also, we can have landscape changes where what used to be not a lot of precipitation pre-fire now causes a significant amount of runoff because the ground has been turned to glass because it burned so intensely. And there's a lot of different ways that a large amount of precipitation can be supplied by the atmosphere too. Let's talk a little bit about those. I'll just give you a few examples. Really good example from last year. I give this presentation. This just happened again, but thankfully not to the same extent. It was the incredible amount of precipitation that fell in the Texas Hill Country over the July 4th holiday in 2025. So near Kerrville, they got about 12 inches of precipitation in 6 hours. That just really happened really, really fast, right? When that amount of water is supplied, it doesn't really matter what your soil's like unless you live on rocks that are really, really loosely splayed out, you're going to have a lot of runoff in a very short amount of time. That's an incredible amount of water, especially over this area. When you think in terms of volumes of water, it's pretty staggering how much water they dealt with. Unfortunate example. Another example of when you get floods is there are persistent events. It's not necessarily that we got 12 inches in 6 hours. It might be you just got a lot of water over a relatively long amount of time. Hurricane Harvey in 2018 is a great example of that as well. So they got about 60 inches of precip in a little bit under a month, where this Category 4 storm, before it made landfall, stalled out because of a stationary front. So it wasn't allowed to move. Typically, hurricanes would interact with the jet stream and take a hard right-hand turn and move off to the east, right? But it wasn't allowed to leave because of these interacting fronts, and it just stalled delivering moisture to the exact same location, Houston, Texas, and caused a significant amount of death and destruction because a large amount of water fell from the sky over a long period of time. So those are just two examples. There's a lot of other ones, as I noted. And these things change in time and in space, depending upon where you're looking. So throughout the entire United States, this is a great paper, by the way, if you guys have never read any of Katie Hirschbeck's stuff. Absolutely awesome. And it's amazing to think that this stuff was published almost 40 years ago. Super insightful. A lot of these things change in space, as shown on the left-hand side, one of the predominant flood seasons throughout the United States. It depends upon how that moisture is delivered by the atmosphere and also how the ground responds to it. But even if you choose a single location, how that predominant flood mechanism or time of floods changes as well, right? A good example of that we got here is in the Puget Sound Cascade region. We went through a lot of effort to derive mixed population flood samples throughout this area, and you can see how those floods are distributed spatially throughout just this region, right? On the eastern side of, or western side of the Cascade, sorry, you have a lot more liquid precipitation that falls from the sky that occurs predominantly in the fall, winter, early spring months, right? There is a good bit of snow, right? But because of the large mountain chain that forms the boundary between the western and eastern portions of this hydrologic area, you get a lot more snow. On the right-hand side, specifically snow melt. There's a lack of liquid precipitation falling from the sky on the eastern side of that watershed. And those have different effects. We need to plan for things differently. We can achieve desirable outcomes in different ways, depending upon those spatial distributions and temporal distributions of flood mechanisms. All right, we go way back, the picture with the dam with the spillway on the left-hand side with water cascading off of it, that was Pathfinder Dam. It's on the North Platte River. Very, very cool. If you've ever been there, it's out in the middle of nowhere, Wyoming, but a very beautiful place to be. Here's another one. Specifically, tell me what type of spillway this is. What is that thing? And have you ever seen another one of these? At least another one that's as big as this one. All right, so let's talk a little bit about how the water cycle, the graphics that I showed earlier, affect flood and flood mechanisms. So floods can be caused, like I said, not just from like a ton of water falling from the sky in a very short amount of time, but also how the land surface responds to that. Maybe the watershed's really, really flat and it takes a very long time for water that falls from the sky and runs off on the ground to get out of the way, right? Or things can happen really fast that there's no time for that water to get out of the way, right? You can also saturate the ground a whole lot, such that there's no more room for infiltration to occur. Everything is saturated, everything runs off than anything that's given to the top, right? Our human action also influences this through infrastructure like this one as well, but also through irrigation, diversion, consumptive uses, right? Humans use a lot of water as well. Sometimes we make flooding less likely to happen because we use a lot of it for municipal and industrial uses in the summer, something like that, right? This interaction with the land surface processes, human actions, whatever else, the interactions between the atmosphere delivering that and what happens on the ground can make even like routine floods that used to be not a big deal in the past catastrophic and we try and do the flip of that, right? So catastrophic amount of water that used to be delivered and cause death and destruction beforehand, we like to lessen that, right? Obviously, we don't want death and destruction to happen. So now we'll get into modeling and how we represent the real world and all the processes that I just talked about in a hydrologic sense. And we'll use this throughout the rest of the presentation as well. This isn't just a hydrologic modeling thing. So why do we model? What is a model, right? In a nutshell, it's a formal representation of a theory. We think something will happen, or we know something is going to happen based upon some empirical evidence like we've seen happen in the real world. We want to represent that to do the what if scenario. What if it rains more than I've seen before? What if I change this area from meadow to parking lot? What is the response going to be like? All these models that we're going to talk about, though, and every model that you've ever seen and will ever see, are simplifications of the real world. It's not that they're useless. That's often misquoted in here as well. But some models are better than others. I'll give it that. Some simplifications are totally fine in certain applications. You can simplify the real world to your heart's content, and you'll get essentially the exact same answers. And then other times where it's like, nah, that's not a good simplification to do for this specific question that I'm trying to answer. Models typically fall in two different categories, one analytical, another one empirical. Analytical is based upon a general set of principles. Think of these as like physically based models or something like that, conceptual models. Empirical models throw that all out the door. They just say, I have this data, I fit a line to it, or I fit a model to that, whatever, and I'm going to use that model to predict how things are going to go in the future. Obviously, that doesn't extrapolate very well. If all I ever saw was like 1 to 3 inches of precipitation, when I use a model that's fit to that to estimate how 10 inches of precipitation is going to respond, all bets are off and how that's going to work, unless you include some sort of reasonable estimation of extrapolation, right? Really good picture here on the right-hand side where we poured dye on that soil, dug it out with a backhoe, and then you can see how different strands of water got into the ground over time. It's not a uniform thing. There's a lot of different flanges that come off of that and look a whole lot different than you would expect if you just drew a simple straight line, right? We'll revisit that one. Remember that picture. So why do we build models? Well, first, and play that what if game, right? I want to make predictions for things that I haven't seen yet. Or maybe it's for things that I would have liked to observe, but nobody was there to observe it, right? Here's a really, really great example of a model. It's a physical model, right? It's a scale thing. I took this picture from our Engineer Research and Development Center in Vicksburg, Mississippi. They're really famous for building a scale model of the entire Mississippi River watershed using German POWs following World War II, right? When we built a lot of infrastructure along the Mississippi River, we wanted to see how the Mississippi was going to respond to that. So we used scale models to make that prediction. They're wild, huge, very, very cool read too if you guys ever want to find out how that was done. We still do that to this day. For really expensive infrastructure, we will make a scale model of the real world and do that what if gaming scenario to figure out how things are going to respond. This is actually a scale model of this Columbia River going through Bonneville Dam. And they were trying different schemes to successfully pass spawning salmon in a more efficient manner, as I recall. But this was like 15 years ago. I'm trying to remember back in my mind exactly what was going on with this one. Problem with this is really expensive. It costs a whole lot. So we typically do this in a computer, right? It's a lot less expensive and maybe a little bit less precise, but it's a lot more malleable and changeable. The predominant modeling system that we use within the Corps of Engineers and really worldwide is the hydrologic modeling system we just develop here at HEC. This model is really like, don't think of HMS as a model in and of itself. HMS allows you to construct models with a lot of different simplifications along the way. It's a modeling system. But again, I'll take it all the way back to what I said earlier. Every one of these models simplifies the real world to in one way, shape, or another. We can answer some really complicated questions with them though, and we can do a lot of we can do a lot of planning and look into the future, look into the past, whatever, more efficiently with numerical models like this. Hydrologic models, one of the main purposes of them is to produce hydrographs or time series of runoff at locations of interest. So they're typically comprised of different components, right, that are best predicted by different processes along the way. More often than not, most folks are interested in the peak discharge, but that may not be everything that is necessary. There's also a rising limb. So how fast does the flood wave arrive at a specific point? There's a falling limb or a recession side. How fast does the flood go away, right? Does it recede? There's also a point at which runoff on the surface, which is this component over here that I term direct runoff, switches from being comprised solely of water on the surface to water that was underground, maybe within the top 6 or so layers, which we term interflow, and also base flow, which is that really slow responding water that takes a long time to worm its way through the ground, but it is eventually water that we have to deal with. All these individual components tie all the way back to our simplification of the hydrologic cycle or the water cycle. We want to represent all of them well more often than not, so we need to simplify all those different bits and pieces according to the system in question. All right, within a hydrologic model, we apply boundary conditions. Think of those as precipitation, temperature. On the outside, they force the model. And then we have those individual processes. You remember back to the flow chart that I had with I think it was a fryer with the bug eyes looking at how complicated it was. All of these individual processes along the way, namely infiltration, transform. Infiltration is the amount of water that goes into the ground or is left on the surface, right? Once that water is left on the surface, we got to transform it into runoff, that direct runoff component. Base flow is the amount of water that goes into the ground, but eventually is going to come back out again. I want to know how long that'll take and where it'll come out. Once water gets into the channel, it's translated and attenuated elsewhere. Got to figure that one out. In addition to man-made things like dams and levees, I got to deal with those too. There are other processes. I don't want to get too crazy at this point in time, but those are the big heavy hitters that I want to try and represent. So let's first talk about boundary conditions. In a modern application, modern hydrologic modeling approach, we're going to be dealing with distributed estimates of precipitation, temperature, things like that. We don't use gauges solely by themselves and say it's uniformly spread over everything much anymore, because there's been a massive proliferation of reliable data, distributed data like this. That's good to go. So precip on the right-hand side, this is for the entire Trinity River watershed in Texas. And then air temperature here on the left-hand side for the Truckee River watershed. We use these all the time. Infiltration in the real world is complicated. Remember that picture that I showed earlier where we poured dye tracer on the soil surface and let it go into the ground and took a backhoe, and you can see how complicated some parts of the soil column allowed water to go through really, really fast while others didn't. It's really computationally difficult to figure out at like an inch scale how much water is going to be going into the ground. Typically, we don't like to wait for answers, right? Or we just don't have the computing power to figure out all of that. So we like to simplify things quite a bit, where I said like, hey, it doesn't look like you can represent all of this water that's going into the ground with like a sharp wetting front. Here's an example of how we do that. One of the more physically based approaches that we utilize quite frequently is the green and amped method. Maybe you looked at this one in undergrad or grad school as well. We simplify that complicated mess down into a sharp wetting front and call it good, for instance. The transform methods that we utilize are typically comprised of synthetic unihydrograph methods. This has been the workhorse since the mid-30s, right? Where we are routing water on the overland plane, so how much water didn't go into the ground, how much water is left on the surface, when is it going to get to this point, and how much is going to be left at that specific time. The most commonly used example of synthetic unihydrographs are from the Clark family, so either regular Clark or modified Clark. You'll see those ones quite frequently, but there's everybody and their brother tends to have a synthetic unihydrograph method. A lot of this stuff is being replaced by 2D routing methods anymore, but unihydrograph methods are really fast, and we like those. Channel routing, this is the difference between depth, right? In the image before, I showed very, very shallow depths that are interacting with essentially every single blade of grass within this watershed, right, or within this channel. Now I have much deeper depths. Now we're firmly in the land of channel routing. I still want to figure out how much water gets to the downstream end or a specific point, and in what time frame is it going to get there. But we use different simplifications of the real world to get there. This is where we start to get into like diffusion wave approximations or full momentum approximations. Maybe you've heard those before. The math isn't terribly different from what we use on the overland plane, but our simplifications of that are usually much less in the channel because we need more information out of that. And dam and levee operations. So we go way back to the image that I showed before. Here's a new one. I'll tell you what that one was. The hole in the lake, that type of spillway is called a morning glory spillway. And that one specifically was in Lake Berryessa, which is just west of us here in Davis, California, in between Davis and Napa in particular. A really cool project to go and see. Normally that's like 50 feet out of the water. It's just this concrete funnel that's coming up. But when the water gets high enough, it spills into that funnel, goes through a closed tunnel, and is discharged downstream of the dam. This is a very different beast here. This is 30 times larger than that, and a very different set of spillway operations here. Name this dam. This one's on the Missouri River in North Dakota, to narrow it down. But this dam controls a massive watershed, hundreds of thousands of square miles, where we can store water temporarily and release it later. Human beings have an incredible amount of play in how water is transmitted upstream to downstream here. We represent the landscape differently within hydrologic models versus hydraulic models. We're after different questions, but there are some commonalities along the way. We use terrain data, like the National Elevation Data Set that the USGS provides, land use information like the NLCD, right? Impervious area estimations, soils, stuff that the USDA provides as well. We take that information and we delineate modeling elements called subbasins. They convert precipitation to runoff. Reaches transmit water. They translate water in time and then attenuate it as well. They handle the open channel flow processes. Junctions combine things together and make it easier for accounting. But we also discretize those individual elements up, typically using gridded processes as well. The smaller that we can get, the more we can take that limit to zero, the more accurate we can get, but we have to pay for it in a computational manner. So floodplain managers can massively help with this data gathering. I can't even begin to tell you the number of times where it's just like, I'm used to using dataset X, and I've had great success with it when I go to do a specific implementation or modeling study somewhere else. And the floodplain manager is like, actually, we have dataset Y here, which better represents the landscape, land use, whatever. I have, because of study that we just did last year, I have very detailed land use information for this watershed, which would be great to incorporate as well. Interact heavily with whoever is doing modeling for you guys. Ask a lot of questions. People may not be aware of what data is out there, but the more data that you have at your fingertips, the better things are going to be. So here's an example of taking that terrain data and looking at flow directions. Then I look at flow accumulation processes, and you can start to see how the watershed is taking shape. And given that flow accumulation and the dendritic network, now I can delineate entire watersheds from that. All right, a model is going to produce outputs, right? The hydrographs that I talked about earlier. An example of that is the blue, solid blue lines. Those are model-derived estimates of flow over time. The black is observed flow over time. This was measured at a USGS gauging station. right? Keep in mind that models are simplifications, and I had initial estimates of a lot of these model states and parameters that came from the data that I just talked about, land use, soils, terrain, things like that. I want to make the blue match with the black. In essence, I want to make sure that my model reproduces reality, right? Can I change everything to make that happen? Sure. But do I really know how precipitation fell throughout the watershed? Do I really know how the soil is best described? Should it be silty loam, or is this more sandy loam or something like that? Uncertainty abounds in modeling. It's difficult to divorce yourself from these processes, and even in a larger sense, we don't really know flow everywhere either. If you ask anybody who operates gauging stations, or especially gauging networks where there's a whole bunch of different locations, they'll tell you like, man, there's a ton of uncertainty in that black line that I'm comparing against here as well. Why are you saying that that's absolute? It should be fuzzy, it should be gray. And typically, like as the line gets bigger or magnitude gets higher, uncertainty starts to rule in here. So we need to incorporate uncertain aspects and not shy away from them, but also effectively communicate them. Further, we'll talk a bit more about that down the road. Some other outputs that we're after in hydrologic models aren't just hydrographs, but I want spatial estimates of rain that fell from the sky, runoff, snow, right? So snow water equivalent is what I'm showing on the left-hand side. That's if I took a column of snow and melted it, how much water would I have to deal with? It's essentially like liquid water equivalent. This is the thing that I need to know for reservoirs, right? Do I have 10 inches of runoff that I'm going to have to deal with if all this melts, or do I only have 3 inches of runoff? That's a big deal. Hydrologic models provide those as well. All right, now we're going to switch gears a little bit and talk about hydraulic principles and hydraulic models. Name this flood. This is an East Coast flood. I don't know if there's any East Coasters out there, but this is a really famous one. This changed how we do flood risk management, not just within the Corps, but throughout the entire country. The last image that I had up there, I believe was, so we talked about Monticello Dam. What was the last one I threw up there? It was this one. So this is Garrison Dam on the Missouri River. Got to take a helicopter ride and see that one time when it was working. This guy is a flood wall along the Susquehanna River in the town of Sunbury. I'm sure you guys don't necessarily recognize it. This is from the 1972 flood, Hurricane Agnes, and killed a lot of people. There was very unfortunate. However, this particular piece of infrastructure performed awesome and saved this town of Sunbury from massive damages. You can see it came right up to the edge. Very, very famous picture of a flood wall. All right, in the realm of hydraulics, we're really studying the motion of fluids, usually water, but it doesn't necessarily have to be just water. We can look at a lot of different types of fluids. But we answer questions like, how deep is water going to get here? How fast is it going to be moving? How long is it going to be here as well, above such and such an elevation or such and such a level? A good example of that here is along the Mendenhall River in Juneau, Alaska. If you guys have tried to keep track of that one, they've been getting a lot of glacial lake outburst floods in the past couple of years, specifically from Suicide Basin, where a ton of water melts, raises ice, releases water catastrophically, and causes a lot of damage here. We want to know, how long is it going to be there? How deep is it going to be? What homes are going to be inundated? How fast is that water going to be moving? How erosive will that water be? Is it going to erode away stream banks as well? Hydraulic models and hydraulic engineers go after this type of information. Similarly to how we use HEC-HMS to answer the hydrologic questions, we use HEC-RAS, which is sister model to HMS, but more tuned to where is water going to be and how deep, right? HEC-RAS is undergoing a transformation right now and a massive amount of modernization effort that's being put into it, going from the old-timey cross-section storage area approaches that are shown on the left-hand side over here to everything is fully two-dimensional, spatially aware of where it is in the world. We're still trying to answer those complicated questions, though, like how deep is the water going to get? How fast is it going to do here, or going to be flowing here? But we do it in a slightly different way using the new meshing approaches in RAS 2025. When you're looking at hydraulic models or hydraulic modeling efforts, you're still dealing with boundary conditions, so those things on the exteriors that are forcing the model, right? And landscape representation that we usually include within the geometry. But now we have a lot more computational options as well because of the simplifications that we make of the real world. But we get to answer some really cool questions along the way. You make some absolutely gorgeous pictures. The first computational option that I want to talk about are steady state approximations. If you guys have ever looked at usually like the old flood insurance studies, anything that was done in the 70s, 80s, early 90s, really, this unsteady modeling didn't come about until the turn of the century. Everything was steady state. What this means is the boundary conditions and properties, channel geometry, all that stuff, they don't change over time. They are static. I'm using essentially normal depth, or not normal depth, but flow approximations and stage approximations, ways that we actually solve for this in a non-time varying way. So because of that, I don't really get to say like how long water is going to be there, how long it'll take for water to get there. There's no really good way to do life loss estimation, but it could still be appropriate for floodplain regulation. This is the worst case inundation scenario. Every nook and cranny of storage has been filled. This is just time invariant, but it still could be appropriate for economic damages as well. More commonly, we look at things in a time varying way, in an unsteady approximation, where the boundary conditions, flow properties, channel geometry can change over time. When we do this, now we can look at how fast floodways arrive, how long they're going to be there. This is really critical to life loss estimation because only a little bit of water flowing really fast can knock you off your feet and take you into a much deeper part of the water floodway as well. We also like to estimate attenuation and translation effects because 1,000 CFS flood wave moving through a channel doesn't always stay at 1,000 CFS. It may reduce and peak as it moves downstream. Really, other important thing too is we want to look at risk estimates for infrastructure, so dams and levees. I want to fail them. I want to see what it would look like had that actually not worked appropriately. I need to do that in a time varying way, so unsteady modeling is the way that we do that. Classical hydraulic models are going to be solely comprised of one-dimensional elements. So the green lines that I'm showing here are all cross sections. Think of those as the computational backbone of this approximation. This is downstream here. This is upstream. I would start at the downstream area and I'll walk backwards up the stream such that this is left, this is right. I'll walk backwards up the stream to compute depths along the way for a given flow rate, right? That doesn't mean that water can't move backwards and upwards. One-dimensional approximations let you do that, but it does simplify things that water can't go sideways, right? And it's also really difficult for us to look at water moving up and down in a cross-section. There are some tricks that you can use to do that, but typically we'll look at flat water surface elevations across cross-sections, and flow is perpendicular to the cross-sections. We can use some storage areas and things that feel like bathtubs on the side. They don't really have any concept of velocity. You get gross approximations here doing a one-dimensional thing, but it is fast is the thing. We can do really, really quick estimations with one-dimensional approximations. You still see a lot of these things out in the wild, though. A lot of our floodplain regulations are built using those. But anymore, we really look a whole lot at two-dimensional approximations where water can go this way or that way, right, or any way in between. This can be computationally intensive, but usually the benefits far outweigh the costs. We discretize the real world up into computational elements, not of cross-sections anymore, but of computational meshes with cells and cell faces, as shown here on the right-hand side. But clearly, we can do a whole lot more with that, where we can look at contraction and expansion. Water will speed up as it goes through a bridge opening. Maybe it overtops a levee to the side and flows left for a little bit, but it doesn't just instantaneously get to a certain point. There is some travel time for it to get there. Two-dimensional is more often the way to go in hydraulic modeling efforts. We're leaving out a dimension as well, but for massive infrastructure that we're trying to look at like millions, billions of dollars, maybe we want to look at three-dimensional approximations where water can not just go this way or that way, but also this way. One great example of that is at spillways, right? Where I can't really get away with the hydrostatic approximations that form the basis of one-dimensional and two-dimensional approximations of flow. I need to look at how fast water is going to be moving and will it actually compress or not, or will it move sideways, or will there be vortices in the vertical direction? This gets really expensive really fast. Sometimes this is the best way to go about gaming out spillway configurations, other things like that. We might also build those physical models that I looked at earlier, like the Bonneville Dam example. We still apply boundary conditions in hydraulic models. An example, we're looking at precipitation on the left-hand side. It is gridded. You can see the rasterization in the precipitation, but I can put water on the top and it'll flow throughout the computational mesh to where it needs to go or where it should go or hydrologically supposed to go. But more often than not, we typically supply boundary conditions that are generated elsewhere, like hydrographs or peak flow rates or distributed estimates of liquid water at the soil surface. So models like, I'll talk more about HEC-SSP up here, but HEC-HMS can feed into RAS. DSS can feed into RAS. There's a lot of different ways that you can put boundary conditions into play in hydraulic models. I mentioned this earlier, but there's a lot of similarities between what we do in hydraulic modeling and hydrologic modeling. We use a lot of similar data, right? So again, floodplain managers can really help with data gathering as well. But we need more stuff in a hydraulic modeling effort than we do in a hydrologic modeling effort. And usually it's much finer resolution data that gets the biggest bang for the buck. We're looking for LiDAR quite often, right? I want 1 foot or 1 meter resolution elevation data because I'm do or die with this type of information for a hydraulic model. I also need a lot of bridge information and constrictions, things that like you don't necessarily get from remote sensing estimates from like airborne LiDAR flights. I might need to see like what the geometry looks like underneath a bridge or something like that. Please help modelers in their efforts to do this in data gathering. There could be tons of data out there that we're just not aware of, and we would make simplifications that we wouldn't necessarily have to make if we knew that it was out there and available for use. All right, here's another good example. If you know what this is, put it in the chat. What are all these circular structures in here? Get some really good estimates of that bathymetry and things that are out there below water surfaces during this modeling effort as well. We'll look at a little bit later. But we need other things like roughness estimates as well. So along this channel or along this overbank, this is what the land use is. Maybe it's coniferous forest, and there's a lot of ground clutter, and I should use this roughness estimate along that way as well. You can get a lot of help along the way and offer a lot of help with a lot of different data sources. Hydraulic models still produce time series estimates of flow, but a lot of times we're really after peak water surface profiles, like those shown on the right-hand side. This is comparing two different geometry alternatives and two different flows on the right-hand side that represent similar situations. So I want to see how high will the water get regardless of time, which how high is it going to get along this infrastructure. So you can do some absolutely amazing things, especially with modern HEC RAS models. This is an example of some modeling that I did for the Arkansas River in Tulsa, Oklahoma. So everything in blue is water that's flowing along the Arkansas River and overtops this levee down here by approximately 2 feet, but doesn't fail the levee. Everything in red to green, I'm showing if the levee fails as it reaches that 2-foot overtopping threshold. So you can compare the differences with and without this infrastructure operating as intended by just looking at the different colors, right? And arrival times, arrival rates, things like that is very, very valuable from a risk management perspective. All right, like I talked about before, we got to tie this back together to some probabilistic expectation. It's cool and all to look at historical events and what if scenarios, but I really need to know how often is such and such a flood going to occur of some magnitude, right? Or the other way around. You can talk about it the other way around as well. But I really want to predict the variability and uncertainty of these certain processes culminating together to produce some sort of a consequential event or sequence of events, right? The purposes of statistical hydrology differ depending upon the question that you're answering. I should say the solution schemes or the ways in which you would go about answering these questions depend upon the question in and of itself. A really common one is like, what's the probability of, let's say, 4 inches of precipitation being equal or exceeded? Well, from a frequency curve, I could choose that value of interest, intersect that frequency curve, and then estimate what its corresponding probability of being equal or exceeded is. I can go the other way around too, right? So there's some planning threshold that I want to know what the 1 in 500 exceedance probability depth is. I can start on the x-axis, intersect that frequency curve estimate, and correspond that with its appropriate y value to say that, hey, there's 6 3/4 of an inch of precipitation is expected to be equal or exceeded once in a 500-year period. First, though, let's talk about this. There's a ton of misinformation out there regarding X-year flood. What is a 100-year flood, right? In a more appropriate sense, it should be termed like the 1% annual exceedance probability. Hopefully you guys have heard this before. When you're amongst friends, don't worry about calling it the 100-year flood, right? But when you're speaking to it, especially in public, I would strongly recommend you refer to it as an annual exceedance probability and speak to it as like, hey, this is a flood that has a 1% chance of being equal or exceeded in any given year. Just because you got a flood of this magnitude this year does not mean that it is impossible of getting a flood of equal magnitude or greater next year, right? This really, really misunderstood concept. A great example of this are floods. I think this is for the Danube River in Germany. I grabbed this image where for a given threshold, the 1% AEP flood stage, they've had that equaled or exceeded once every 37 years, all the way up to once every 192 years, right? There could be a 192-year period where you just don't get a flood of that magnitude. But there can also be multiple occurrences within a 100-year period as well. In fact, the probability of getting a 100-year flood or 1% annual exceedance probability flood in the life of a mortgage in 30 years is actually 26%, which is pretty wild to think about and hits home pretty heavily, right? That also changes our estimates of what that flood is, that magnitude of flood change over time. We typically perform flood frequency assessments following big floods, which kind of stinks because that's when they change the most. This is not a hard and fast thing that we know truly what nature can provide. We use observations to estimate what nature can do, right? So the blue dots along here are the annual maximum series, the largest flood in any given year for the specific location. And the red line is our time-dependent estimate of the 1% AP flood. And you can see that it's chugging along to start with, and then I have this really big flood in 1955 that absolutely jacks up our estimates of what that flood is. And then it tends to settle back down over time as well because we don't get these extremely rare floods over and over again. But when do I assess flood frequency? Typically, following big floods, right? Massive damage, depth, and despair happen after these big floods. We want to know how often that's going to occur. That's when they change the most, which is pretty unfortunate, but that's the way that we go. We can assess flood frequency from the data itself, right? A really good way to do that is to look at every single year's biggest flood, the annual maximum or the annual maxima. Say I had 85 years worth of data that I could pull from the USGS. I take the largest floods and every other flood, and I construct what's called empirical distribution. First, I slide the largest flood over, and I assess its relative probability to the rest. And a very easy estimate of that is 1 over the sample size plus 1. So in this case, it's 1 over 86. I do that for the rest of the series. Maybe I just start with the top. And I can assess its what we call plotting position along the way. So the 38th largest flood has a relative probability of 38 out of 86. I do that for the remainder of the series. And now I can draw a line through the rest of them, right? This is an empirical frequency curve, an empirical estimate of the relative likelihood of a flood of such and such a magnitude happening. But what's the likelihood that a flood greater than 9,000 CFS is going to occur? Don't really know. Because this is an empirical model, an empirical estimate, I cannot extrapolate very well. In the US, we use heavily analytical methods to make those estimations. And this is very, very common practice throughout the world where analytical methods are used to infer the relative likelihood of floods happening. But the very specific thing to the US is that we have these guidelines that are determined or published here that people should follow in these different types of studies within a document called Bulletin 17C, where we fit a specific distribution, a log Pearson 3 distribution, with a specific fitting method of the expected moments algorithm. There's a lot more details that go into it than that, but that allows us to infer flood frequency throughout the entire range of probabilities. So given those methods, we can estimate flood frequency like those that are shown on the left-hand side here, from probabilities of 1 all the way to 0, or near 1, near 0 as well. Very, very, very rare. We can extrapolate beyond the range of observed data. I can also do other fancy things with that. I'm going to show here on the right-hand side. We can talk more about later if you're interested. But I also need to estimate flood frequency at not gauged locations, ungauged locations, right? So here's where I grew up in Pennsylvania, nowhere near a gauge, but I still need to estimate flood frequency. A really quick and easy way to do that is with regional regression equations, which are formulated upon a lot of those Bulletin 17C estimates I was talking about before, but conceptualized in a regional manner. StreamStats is an amazing application, an amazing platform to use to do this. It's available all throughout the US. Please go and check that out. The USGS supports that heavily. I can also tie together hydrologic and hydraulic models to estimate flood frequency. 100%. We do this all the time. There's a lot of different schools of thought on how to do this, though. You can introduce a lot of complexity along the way, or simplifications can introduce limitations as well. We can talk a whole lot about that. But we pull it all together, all the hydrologic modeling concepts I talked about earlier, all the hydraulic modeling concepts I talked about earlier, put them all together, and I can estimate things like runoff likelihood, flow frequency on the left-hand side here. Right, this is a hydrologic model that's estimating runoff. In particular, visualizing SWE here. This is the Duwamish River watershed. I can apply that in a hydraulic model and estimate inundation depths or stage frequency, which is visualized there on the right-hand side. The stage frequency I can then use to regulate floodplains or make inferences of actions that I should take from a probabilistic perspective. I threw a lot at you really, really quick. I know. I don't want to just be like, okay, go forth and conquer. There's a lot of resources to reach out for, especially within the Army Corps of Engineers. We are always willing to partner, especially through the Silver Jackets program, with non-federal sponsors as well. That's what we're here to do, right? I work at the Hydrologic Engineering Center here in Davis, California. We serve the entirety of USACE and worldwide as well. We also have the Risk Management Center, which is specifically tuned to dam and levee safety considerations, and the Modeling, Mapping, and Consequences Center, and the Engineer Research and Development Center in Vicksburg, Mississippi. And talked about them earlier. A lot of districts throughout the entire country and divisions with a lot of different resources behind them as well. If you don't feel like reaching out, go and check out our website. I throw a lot of links in here as well. We have tons of documentation, use cases, short 5-minute YouTube videos that give you snippets of information along the way. We've done countless webinars as well with a ton of different topics, all hydrologic, hydraulic, consequence, statistical hydrology concepts are in there too. Please go and hit these up. I'll provide this presentation you guys can look at later as well, but I point you in that direction as well. We've likely written a tutorial about the question that you're going to ask. Hit that up. So I gave you a lot really quickly. There's like 4 minutes left. I'm here to answer your questions. as well if you do have them. If you feel like answering or asking them later as well, I'm always willing to answer emails. I'll include my email and all my correspondence to Lenny as well. She can give that out to you guys. We talked a lot about hydrology, hydraulics, and statistical hydrology. They can really be summarized into like how much water is going to get to a specific point and when for hydrology. For hydraulics, it's going to be like how deep is water going to get, how wide is the floodway going to look like, and how fast is it going to be flowing. And then statistical hydrology ties that together with the probabilistic concepts of like, okay, so how often is this flood of some magnitude expected to occur? So we have to answer really complicated questions like what's the likelihood of such and such a levee or structure exceeding this probabilistic flood with a certain amount of assurance. You got to do all three of those things together to answer that question. There's a lot of resources out there to help as well. Do you have any questions? Anything in particular that you guys would like to talk about?